In Chapter 2, we spent a good deal of time looking at linear functions. Chapter 3 is going to take a look at a different type of functions called power functions and polynomial functions. This first video is going to be vocabulary heavy as we start taking a look at these new power functions and polynomial functions, and then we'll start getting into more mathy things as the chapter progresses. First, we're going to look at the power function. A power function is any function that can be written as f of x equals x raised to some power. Now that is where it gets its name, and there are some characteristics of power functions. Specifically, when we're looking at their graphs, it depends on if that exponent is even or odd. First, let's look at even power functions. If I look at the graph of an even power function, let's say x squared, we end up with this nice little graph here. If I were to take a look at the graph of another even power function, such as x to the fourth power, again an even, what we'll see is the graph looks very similar, just a little skinnier. And we could keep going with x to the sixth power, and we'll see there the graph gets even skinnier, but still has that same basic shape. Now we might try and describe these even power functions, and one way we try to describe them is we try to describe their end behavior. When describing the end behavior, we're interested in what's happening at the ends of the graph. So as the x's here are going off to the left side at negative infinity, you see all these graphs off to the left side are going very high, way up. You see the graph is going up. The way we show this with our notation is we say that as x goes to negative infinity, the function or the graph is going to go up to positive infinity. And you'll notice the similar thing happens as we go off the right side to positive infinity on the x, the graph is still going up. As we go off to positive infinity, the graph still goes up on the right side. So as x goes to positive infinity, the whole function does the same thing. It goes to positive infinity. On the ends, it's going up to infinity on both the negative and positive side. Now we could contrast that with the characteristics of our odd powers. Let's draw a few graphs of these. These are just going to be rough sketches, but I'm going to start with x to the first power, which is going to be this guy, x to the third power, which comes up, flattens out, and goes up, and x to the fifth power, which comes up even steeper, flattens out, and goes up even steeper. Now here, you notice our end behaviors are doing something slightly different. With these odds, as x goes to negative infinity, if we go off the left side of the graph, where does the graph go? This time the graph goes down. So with these odd power functions, f of x goes to negative infinity if we're on the left side. And if x goes to positive infinity, then f of x on the right side, here you notice it goes up on the right side. So the f of x is going to positive infinity. That is the end behavior of the odd power functions. Now, one little wrench we can throw into this process is if we put negatives in front of things. And we know from our prior chapter that a negative will flip the graph vertically. So now if I have negative x to the fourth, well, x to the fourth used to be a U shape going up. negative x to the fourth. Negative x to the fourth is going to be a U shape going down, which means now as, again with our long-term behavior, as x goes to negative infinity off to the left, the graph goes down. F of x also goes to negative infinity. And as x goes to positive infinity on the right, the graph goes down. F of x goes to negative infinity on the right. It's going down on both directions. We could even do a negative odd. Let's do negative x cubed. X cubed came in from the bottom, leveled off, and went out the top. Well, now it's going to flip over, and it's going to look like this, which means our long-term behavior is as x goes to negative infinity off the left side, the graph goes up, so f of x goes to positive infinity. And as x goes to positive infinity on the right, the graph goes down. So f of x goes to negative infinity. And that's kind of the long-term behavior of our power functions. Now, power functions aren't as interesting to us because they're really the basic form of what we call polynomial functions. And that's where we're going to spend most of our time, is working with polynomial functions in this chapter. Now, a polynomial function is simply just a sum of power functions. Let's say we've got f of x equals 8x cubed minus 3x squared plus 4x minus 2. This is a polynomial because there's 4 power functions added and subtracted together. A little bit of vocabulary around these polynomial functions. And we're going to use this blue example up above to set up the vocabulary. First, we're going to talk about this term coefficient. A coefficient is simply the number in front of the variables. So for example, in the 8x cubed, the coefficient there is 8. In negative 3x squared, the coefficient there is negative 3. One that's not on here, if I just had like x to the 7th power and there's no number written in front, we always assume there's an invisible 1 in front of everything. And so for this one, the coefficient would just be 1. If nothing's written, the coefficient is 1. Next word we want to define is term. Terms are things that are separated by addition or subtraction. So in other words, if we were to list the terms of this blue polynomial, 8x cubed would be a term because it's separated by a minus. The negative 3x squared would also be a term, and notice with the terms, the negative comes with it. 4x would be another term. Negative 2 would be another term. If I want to know the degree of the polynomial, degrees of polynomials are the highest exponent that we see. In this case, we'll see that the highest exponent in the entire problem is that 8x cubed. So we would say this is a 3rd degree polynomial because that's the highest exponent. And the degrees tell us a lot about how the graph behaves, and we'll get into that in a minute. The leading term The leading term is the term with the highest power. So we already said cubed was the degree, so that term is 8x cubed. That's the leading term. And often with that leading term, we're really interested in that leading coefficient. The leading coefficient is the coefficient of the leading term. And so if 8x cubed is the leading term, 8 is the leading coefficient. Told you today was heavy in vocabulary, so we make sure we know what we're talking about when we work with these polynomials. Now we talked about long-run behavior of the power functions. We can look at long-run behavior of polynomials as well. And it turns out the long-run behavior will follow the leading term. So if I have a polynomial like negative 2x to the fifth plus 3x squared minus 7x plus 1, I know this is going to behave as if it was the leading term all by itself. So if I were to draw a graph, I know 2x to the fifth, because it's negative, comes in from the top. And I don't know what happens in the middle, but I also know it goes out at the bottom. It might wiggle around in here somewhere. This stuff we don't know about yet. But what I do know is off the left side, it's going to be positive. Off the right side, it's going to be negative. In other words, as x goes to infinity, f of x is going to go to, let's put a negative in front of it so we're clear. As we go off the left side, x to negative infinity, the graph will go up, f of x will go to positive infinity. And as x goes to positive infinity off the right side, the function will go down to negative infinity because it is odd and negative, just like our power functions that were odd and negative. Now I mentioned we don't really know what happens in the middle here. That's a big question. So that kind of leads us to our short run behavior. Couple things that we know about short run behavior. First thing we're going to talk about with short run behavior is that each power bends the graph. Now here's what I mean by that. If I have a graph that comes in, maybe bends up, comes back down, bends up, comes back down, and I wanted to know what is the degree of this polynomial. Well, I know that we're entering from one side. That's my first degree. Then when I bend up, that's our second degree. Then it bends down, that's the third degree. Then it bends up, that's the fourth degree. And then it bends down, that's a fifth degree. So that tells me this graph is a fifth degree polynomial. If I were to try and graph a third degree polynomial, say I want a third degree. And I just wanted to graph any old third degree polynomial. I can come in from one side, there's one, bend, there's two, bend, there's three. And so I know a third degree polynomial is going to look something like this because it has three bends. Another thing we might be interested in with the graph, though, is what about where it crosses the x and y axis? Those are called intercepts, and those intercepts can tell us a lot about the graph as well. Intercepts. Cross the axis where the other variable is 0. Here's what I mean. F of x equals 2 times x plus 1 times x minus 3 times x plus 2. If I wanted to find the f of x intercepts, or the y intercepts, remember y is the f of x part, we can make x equals 0. Then I make x equals 0, f of 0, 2 times 0 plus 1 times 0 minus 3 times 0 plus 2. Well, that's really easy. That's 2 times 1 times negative 3 times 2. And that adds up, or multiplies, to negative 12. So the y-intercept for this problem is negative 12 because I made the x's equal to 0. We can find the x-intercept as well. That's where we make the other variable 0. We make the f of x equals 0. That's going to give us 0 equals 2 times x plus 1 times x minus 3 times x plus 2. Now this is really nice for us because it is completely factored. When we have two factors, just kind of as an aside, if I have two things that multiply together, or more than two things that multiply together and equal 0, I know either the first factor equals 0 or the second factor equals 0. Because that's the only way to get 0 as an answer when we're multiplying. One of the parts has to be 0. Well, here I've got 4 parts, a 2, an x plus 1, an x minus 3, and an x plus 2. Now the first factor, 2, is clearly not a 0, because there's no variable there. But the other 3 factors could be, and so what I can do is I can set up an equation where the first factor equals 0, the second factor equals 0, and the third factor equals 0. And I can solve each of these quickly by subtracting 1, adding 3, and subtracting 2. And that's going to give us 3 x's. That means this graph has 3 x-intercepts. Now with the information that I have for this graph, I know that there is an x-intercept at negative 1, 3, and negative 2. I know that there's a y-intercept down here at negative 12. And then I can connect the dots where I'm not allowed to cross the graph anywhere else, except at those points. And I know the graph of this line looks something like this, and we're starting to kind of get an idea of how we can build these graphs by knowing their degree, by knowing their end behavior, and by knowing their short-term behavior. Now it's your turn to practice just kind of working with this vocabulary and applying it, and then we'll look at it more mathematically in our future videos.